All right, here is the helpful link for all the stuff we're going to talk about right now. It's what everybody uses most of the time because it's a much more concise version of what you can find in the textbooks and the how to make planes books and whatever. So in case I say some like variables or you see them and you don't know what they are, they're all listed out at the top. And there's some diagrams, and where we're going right now is probably to the second page where it talks about, or where it's showing, the header says center of gravity position, but what we're looking at is this diagram with all the various behaviors that you'll get for different static margins. And hopefully my screen is also showing that. So basically, the main kind of stability we worry about for the kind of planes that we make, at least, is pitch stability, because it directly affects and is dependent on how much lift you're producing and where. And so it's the strongest, it's the one that's most impacted by your performance and has the greatest impact on your performance. Because if you design a very a plane that has bad stability characteristics, then you have to waste a lot of your performance on correcting them in flight. Whereas if you design a plane that has good stability characteristics, then you leave yourself as much performance as possible for doing good performance instead of dealing with your bad stability. So the center of gravity, in case anyone forgot, is marked on all these diagrams as this little dot, but it's the place where all the mass could be concentrated to, the mass of the aircraft could be concentrated to a single point, and it would have like the same location, I guess, as the distribution of the mass of all of the, like as it is normally as the plane, which means it's also where the gravitational force can be thought to apply in the system. And so when we build the plane, once it's built, you usually can't move like the general like locations of the lifting surfaces. Sometimes you can change their shape a little with control surfaces to create different forces and stuff, but you can't like move them forwards and backwards and twist them around and stuff very much. So basically that means you try to place the center of gravity in a location that will give you the desirable stability characteristics. And for most conventional aircraft, that position is within the like longitudinal chord like distance of the wing. So it's somewhere between the leading and trailing edge of the wing. And specifically for like highly conventional aircraft, like what your guys' design looks like and what a lot of DBF designs look like, it's about a quarter of the way, like a quarter to a third of the way back from the leading edge of the wing. But that rule of thumb, again, applies specifically to planes that look like this, that have a single main wing and a tail. And then the difference between, oh yeah, so that's the CG and its position. Then the other relevant point is called the neutral point, and I think it defines that on here. Oh yeah, so the neutral point is called that because if you put the CG there, then you have neutral stability, which means that if the aircraft is flying straight and level, it has no well, it basically means that you, it means that regardless of your aircraft like flight condition, so whether it's straight and level or becomes pitched up or becomes pitched down or whatever, the aero forces like all apply at that point basically. So sometimes it's also referred, like these aren't all exactly the same thing, but it's also generally the center of pressure or the center of lift, which like those three things can be different, but basically it's the same thing as the center of gravity, but for the like pressure or lifting or drag forces on the aircraft, so that at that point is where you can consider all of the aerodynamic forces on the plane to be concentrated. And so hopefully it makes sense that if you were to put those over the top of each other, then nothing you change about the flight conditions, which would then change the aerodynamic forces, will change the like the motion of the plane based on changing the flight conditions. Because if you imagine those points aren't at the same place, so the CG is somewhere and the CL is, or like the CP is somewhere else, then if you were to change your flight conditions and your aerodynamic forces changed, you would now have a moment about the center of gravity due to the different aerodynamic forces. And so that moment would then start to change the motion of the aircraft. So the reason you need to understand that is that the relevant characteristic that we're trying to create is called the static margin, stability margin, or static margin if you're talking about static stability. And it's derived with this formula, which is basically the difference in distance between the those 2 points, usually measured from either a datum or the nose or whatever. So the distance, or basically the x coordinate of the neutral point and of the CG, that difference normalized to the chord, so that we can apply this to any plane. And so when you have a stability margin, or since we're mostly talking about static stability here, I think, yeah, if you set that to within a certain range, then you'll get a certain predictable stability behavior, which basically means that if you apply what they call an upset, so like you're flying along straight and level, steady, and then like all of a sudden the nose is just pitched up like a little, whether it's by a gust of wind or just by magic or whatever, then how does the plane respond? So if you have a 0 stability margin, then that means that these are right on top of each other. And like I said, that means that when you change the aerodynamic forces, which they'll change because you'll start to slow down and for a little bit you're at an angle of attack or whatever, that doesn't actually influence the motion of the aircraft, even though the forces change, because that difference in force can't create a moment about the center of gravity because it's aligned with the center of gravity. Whereas if your center of gravity is in front of that point, then let's say you get the pitch up moment, your aero forces are going to increase, like be positive, which will create a nose down moment and cause you to pitch back down as those forces increase. So that means it basically creates a restoring force if your center of gravity is in front of your center of pressure. And the farther in front of it is, the greater that restoring force. So like an extreme example of this is like a dart. A dart has its mass mostly in the front and its like aerodynamic surfaces in the back. And so if a dart is flying along straight and level and you deflect it nose up, all the aerodynamic surfaces are going to create an upward force because they're deflected downward into the airstream. and they all have like a positive angle of attack, so they create an upward force that pushes the tail up, and that's the moment that pushes the nose back down and returns it towards level flight. And the same thing will happen in the opposite direction. Whereas if you imagine trying to throw a dart backwards, which is the extreme opposite example, then as soon as you throw the dart, even if you throw it like perfectly straight, any perturbance at all will deflect the fins, and then they're like, let's say the front of the thing with all the fins on it deflects up. That's still creating an upward force, but now the upward force is a moment about the CG that's way in the back. And so it's going to want to continue going that direction. And the farther it goes in that direction, the greater the force gets. So it's a self-reinforcing force, which would then make the dart like flip around and fly the correct direction. But you can have a plane that looks mostly like a plane, but if the tail basically, or yeah, so still focusing on the neutral point, if the neutral point is ahead of the center of gravity, then when it tries to fly forward, the aero forces are trying to flip it around to fly what the direction that puts the center of gravity in front of the neutral point. So that's why this is important, because you can make a plane that will fly even if it's unstable, but it requires continuous control adjustments to keep the nose pointing forward. And we're talking like continuous enough that you have to have a computer do it. So aircraft that don't have fly-by-wire basically can't be unstable because humans can't react fast enough for that. And the only aircraft that fly that are unstable are all fly-by-wire, and the pilot isn't controlling the flight controls. They're telling the computer what they want to do, and the computer is controlling the flight controls. So we want stable aircraft, since we can't have like computers flying the plane at our level. But the degree of stability will determine like how you try to size the tail. And so now I think we can get on to actually doing that. But yeah, so these the stability margin, static margin values are since they're normalized to the chord, these will apply to any aircraft. This pretty much applies regardless of configuration. It's just that the rules of thumb that I'm stating do depend on configuration, but because the static margin, like this concept, applies to any vehicle in flight, it could be a missile or whatever. It doesn't have to be a plane. It doesn't have to have this layout. It's just depends on the neutral point. Okay. Yeah, and in addition to like changing the pitch then changes the angle of attack. Hopefully you can envision that. But you have to remember that changing the speed also changes the lift, because in the lift equation, the CL changes if you change the angle of attack, because CL is dependent on angle of attack. But if you stay in level flight, you're not changing the CL, but you can still change the speed and your lift will still change, which will then mean a change in your lift force, which then applies still to changing the motion of the plane. At neutral static margin, your direction won't change, and then stable and strongly stable. At unstable, it still does the opposite things. They just didn't draw it here. So like if you increase your speed and have an unstable thing, then it'll still change the lift. It'll just like flip you around because it'll do the same thing. And I'm pretty sure the problem is not just that if you increase your speed at all, then the lift force like flips you around due to the speed. It's just that that initial change from the speed changing would be enough to create an angle of attack that would then flip you around. Whereas like this change will happen even though, since it's stable, the angle of attack increasing doesn't necessarily doesn't necessarily like force it to diverge since it's a stable design. It's just that as the speed increases, the trim condition, which I think we'll talk about today, the trim condition changes. So unless you retrim, you're now out of trim, and so it wants to fly at a new like pitch setting basically, since you're at a higher speed. Okay, yeah, I guess we can talk about trim right now. So if you don't know what trim is, it's basically like a small change to the control surface that makes it so that you don't have to provide a continuous large change to the control surface. And the goal of trim is to keep you flying in the condition that you are currently flying in. So if you look on here, ailerons, rudders, and elevators can all have trim tabs, which is one way of implementing trim. And it's basically like a tiny control surface inside the bigger control surface. And it works by deflecting the opposite direction from how you want the control surface to move. So like, let's say I want to trim my nose to be more up, then that means I want the elevator to go more up, because if it goes up, the tail will go down and the nose will go up. So that means I actually want the trim tab to go down, because if I push the trim tab down, that'll push the elevator up, which will push the nose down, which will push the nose up. I think I said nose too many times there, but basically that's how trim tabs work. But not all control surfaces use trim tabs, although I Googled that, so that's all we're going to see probably. But there are some systems that just make it so that it like adds in the trim setting in addition to whatever the normal control setting is. So if your elevators, if your like flight controls are set to neutral, then the elevator would be neutral. But if you tell it to trim nose up, then even when the flight controls are neutral, it'll just set the whole elevator to be slightly up to push the nose down to push the nose up. I mean, the tail down. I keep saying nose twice, but to push the tail down to push the nose up, it'll just shift the whole elevator up a tiny bit, like less than you would normally see when you move the flight controls, but enough that it still impacts the flight direction. And that's more common on newer things because you basically do need a computer to do that. But that's actually how our trim systems work on our planes, because they're flown through like an electronic system. Even though it's not a fly-by-wire, the transmitter is still just sending a proportional signal from like -1 to 1 basically to the receiver on the plane, and then that signal just gets converted to a PWM signal for the servo to actuate to. And so if we want to trim, the transmitter just mixes in the trim signal with the like standard flight control signal, and then when the receiver gets that, it doesn't care like if you're trimmed or not. It just always takes whatever control input it's being given and sends that to the servo. And so the transmitter can just say, I want like, the flight controls say neutral elevator, but there's a little nose up trim also. So I'm just gonna put it at like 1% nose up, or like basically this servo go 1% up or something. So we don't use trim tabs for that reason, but we still have the ability to trim our planes. And so the trim condition is the one where you don't need to hold the primary flight controls, so they can be at neutral and you're still flying usually straight and level, but you can trim for a turn or whatever. So that understanding that is why, or is good, because if you are strongly stable, then you need more trim to like be able to fly straight and level at the same range of speeds. Whereas if you're closer to like, because if you're at 0 static margin, then you never need trim to keep flying the way you're pointing basically, because the aero forces aren't changing as your speed changes. So you can like it says here, you can speed up and you don't start to change your motion never changes, because even though the aero forces are changing, they're not creating a moment. The reason you need trim on stable aircraft is because as they speed up or slow down, the aero forces change and the lift moment changes. And so you need the trim to account for that change in moment. And this is what I was saying about wasted performance, because if your aircraft is so strongly stable that you need a ton of trim to maintain straight and level, then all of this, like that, since basically when you're deflecting your tail, you're creating lift, that means you're also creating drag, more drag than if you have zero deflection. And the more trim you need, the more drag you're creating. So that's wasted performance, basically. So one goal is to require the least amount of trim, but at the same time, you want the plane to be stable. Okay, so now we're finally getting to desirable numbers. So in general, you want your static margin, stability margin, whatever, to be somewhere between 0.05 and 0.15. And the closer you are to 0.15, the more trim you'll need, but the more stable you'll be. And the closer you are to 0.05, the less trim you'll need, but the less stable you'll be. I don't know if it mentions it in here, but there's some other characteristics associated with stability. So the more stable your plane is, the harder it is to stall and the easier it is to recover from stall. But the greater control inputs are required to achieve the same like difference in motion. So the same thing is with the trim. If I suddenly want to, or like if my plane is strongly stable and I want to pull 2 Gs, then I need a lot of control deflection because the plane is trying very hard to restore me to like straight and level flight. If I am weakly stable and I want to pull 2 Gs, I don't need as much control deflection because the plane isn't trying as hard to restore me to straight and level flight. And so the other benefit of being weakly stable is the plane is more maneuverable, basically. So it's for a given control deflection, it'll maneuver more intensely, more greatly, I guess. And for your total range of control deflection, you can get more maneuverability out of the aircraft than you can if it's more stable. For example, a dart is very unmaneuverable. Even if you made the little fins like movable, you'd have a hard time steering it because it doesn't want to turn very much. Whereas, well, yeah, there's not that many things we think of that have like zero static margin, but I guess you could kind of also think of it with like something that has wheels. So like a unicycle, when going forward, basically has zero static margin because any way you turn the wheel, that's immediately the direction that the thing's going to go. Whereas like if you, actually that might have been a terrible example because I think if you put the wheels on the back of the turning wheels on the back of a car, it's harder to drive or something. But anyway, yeah. Well, I forgot where I was going with that, but basically we can get to actual sizing the tail now. So yeah, we're starting with horizontal because again, pitch stability is our biggest consideration. And so the way that when you're first doing the design, since you can assume that you're going to want to put the center of gravity somewhere around the quarter chord of the wing. In order to do that, like to make that feasible, you want to design the plane so that its neutral point ends up in a spot that will let you get your desired static stability. And the reason a lot of these are ranges is because like you might have a wing or something that is farther one way or the other because of your performance requirements, or your fuselage might make it harder to put your CG in a certain position or whatever. So you can go to like different ends of the ranges of these different characteristics to try and balance out your final performance and stability and everything. But so the parameters that go into sizing your tail are the area of the tail surface. So I'm going to call it the elevator a lot probably, but technically you have like multiple parts. So the whole, bro, I swear to God. So hey, look, it's talking about trim. There we go. So basically everything behind the end of the fuselage is, or that has to do with control, is called the empennage. So this whole thing is the empennage. And usually for planes like ours, especially, it's made up of 4 relatively distinct parts. And lots of things have different names. And the reason it's good to know the names is it helps you make sure everyone's talking about the same thing. So the whole top piece is generally called the fin. And if you're just talking about the part that doesn't move, you're generally call it the vertical stabilizer, because you don't need any control surface there and it'll still stabilize your vertical axis. And then the control surface on the back of the vertical stabilizer is called the rudder. For the horizontal, I thought there might have been a word somewhere, but I usually just call the whole thing the horizontal, and then the non-moving part is the horizontal stabilizer, because again, with no elevator, it would still provide stability. You just wouldn't be able to like control it. And the part on the back of that is called the elevator. If we also talk about ailerons, those are, in case you haven't seen them, they're the little, come on, good picture, there we go. They're the control surfaces on the wing tips on the back, closer to the tips. The ones closer to the root are usually where the flaps are, but so yeah, so this S is the area of your entire horizontal tail surface, and then the L is the distance between the aerodynamic center of the horizontal tail surface and the aerodynamic center of the wing, which is always often, I don't know. Well, that's what these pictures are for. So LH, oh, sorry, I guess it's to the CG. I should stop telling people that it's not then. Oh yeah, okay, so it's just the moment arm for that. So amended, the LH is the distance from the aerodynamic center of the tail, the horizontal tail surface, to the center of gravity, which makes it a moment arm. So basically this is the distance at which the tail's lifting force is being applied, since that the aerodynamic center of a lifting surface is like the center of pressure just for that surface, basically. So if you wanted to like apply the whole lift force from that surface at one point, it would be the aerodynamic center. So this is the arm for that force. And then it's divided by the area of the wing. So that's this S, and the chord of the wing. So that's C. And then that formula is VH, which is the horizontal tail volume coefficient. And it's a coefficient, so it doesn't have units, but basically you can think of it as like the overall size of the tail. So that doesn't really say anything about the shape, just like how the wing area doesn't say anything about the shape, but it factors in that the tail needs to have like a certain complete picture of its size in order to balance with the wing. And so the desired range of values for like, that's based on this basically, is 0.3 to 0.6. And so if you put that on the left side and then put in this stuff, which you should already know from, on the right side, then you can basically vary either of these to get a tail that will give you your desired stability, which means you could either make the surface, it's not like surface area because not both sides, but basically the planform area of the tail you can make that bigger and then make the arm smaller, so move it closer, and you would get more, or you would get enough stability. So if you think about like, if I bring this thing closer, then I need it to be bigger to generate a bigger force at a smaller moment arm. But if I move it farther away, then I don't need as big of a force because I have a longer moment arm, so I can make it smaller. And that's why these are inversely proportional to each other. And so it's saying like, blah, blah, blah. Smaller basically means less stable and bigger means more stable. And that goes into figuring out your neutral point, which means you can also decide a neutral point if you want, or at least you can decide a static margin and then factor that in there. And then, yeah, so anytime you see this subscript h, that's going to mean the tail, the horizontal tail. And just like the wing, it doesn't just mean one side. So it's not just this, it's the entire horizontal tail. So the aspect ratio would be like, I don't know, like 4:1, not 2:1. Yeah, so that's the horizontal tail. And then the vertical tail works much the same, but I know we haven't really talked about vertical stability, like vertical axis stability, but basically it explains it very simply here, which is if you didn't have a vertical tail, then when the plane's trying to fly forward, it could basically just start to spin around the vertical axis because there's not really any forces like keeping the tail pointing backwards and the nose pointing forwards. And so if the airflow is going this way, if you put the vertical tail at the back, or like the fin at the back, basically, then if the tail starts to deflect that way, it generates a force the opposite direction and gets pushed back to center. And the rudder is just the movable part of that, so that you can change that on purpose if you want. But so then you come up with a vertical tail volume coefficient, which works the same way. This time it's based on the area of the wing and the span of the wing instead of the chord. And the other factors are the area of the fin and the arm from the aerodynamic center of the fin to the center of gravity. And so again, you can vary one of these and the other one will go in the opposite direction because closer equals need more force, farther equals need less force. And this is the range that you generally want for your vertical tail, 0.02 to 0.05. And then it briefly describes the characteristics of having low vertical stability versus high vertical stability. And there's not really a great reason to have too low vertical stability. It's just that the more stable you want to be in the vertical axis, the heavier the rudder will get. So there's no reason to make it huge, but yeah, but since we have the aileron, like this becomes more important if you only have a rudder to execute turns with, because then you need to be generating a pretty reasonable force to both push your nose over and get yourself rolling, but we don't do that. So just kind of stick with this and do whatever makes sense here. And a lot of times, as you might have noticed, the vertical and horizontal tails tend to be located at about the same moment arm. And honestly, that's, in my experience, pretty much just because it's easier than like building, I don't know, but if you wanted to put like the, basically one of these will be better if you put it farther away, but for the other one, if you put it closer, you're just like adding weight because you're making it bigger. And so generally you can just size it to whichever one should be farther away, or you want to be farther away, and then put the other one there too, because that'll just allow you to make it smaller. So, because otherwise you just have like a longer tail boom, and then one thing is sitting way out at the end, and then it's like, why didn't we put the other one that far away too and make it lighter? So that's why they're usually around the same location, which means they have roughly the same moment arm usually. And so this also talks about some other types of stability. Dihedral is the angle between between horizontal and the span, like half span angle. And it basically makes you slightly roll stable so that you don't, so that if you put in roll, it won't just stay there or get worse. It'll like slowly roll back to level, but we don't build that very often, partially because it's a little bit harder to like build the structure for that, especially the wing attachment structure, compared to if it's just level. And we usually fly fast enough anyway that you're turning often enough that the dihedral wouldn't really have a chance to like work either. So we don't worry about dihedral too much. Yeah, and so this is talked like dihedral is definitely important if you only have rudder for control, but we have ailerons, so don't care. More dihedral stuff. Yeah, and so another thing that's good to know in case you didn't is that, or well, I think I said this before, but like planes don't turn by just pushing the rudder sideways and then pushing the nose sideways and then suddenly magically traveling in that direction. They turn by rolling to a non-level bank angle, and then when the nose would want to then drop, you just hold the nose level, and by doing that, you're also pulling it in the direction that you rolled. So if the plane were to like roll left, then the nose would want to drop and you hold it up with the elevator. So you don't really use the rudder when you're turning very much. You do a little bit, but I'll get to that in a second. Instead of the nose dropping, you pull the elevator up and that pulls the nose up. But because you're not like the nose up, like pitch up direction is no longer directly up, it's also up and sideways. And that sideways movement is what turns you. So the only thing you really use the rudder for is called adverse yaw, which hopefully I can find it. And you can use it for slips and stuff, but in like normal flight. So when you use the ailerons, because you're oh yeah, I guess I could explain this about all control surfaces, but all you're doing when you move a control surface, if you think about it, is just changing the camber of the airfoil from leading edge to trailing edge. Because if you deflect that control surface up, then the camber has just, or sorry, not even the camber, but the camber and the angle of attack. Because if you remember, the angle of attack is the line between the chord line and the free stream. And when you move the control surface, you're literally moving the chord line as well. So, and it can change the camber too, I guess. Yeah, it changes them at the same time, but you're basically changing the shape of the airfoil by moving the control surface. And so that's going to change how much lift you're generating and in which direction. And so with an aileron, let's say I want, like this plane is trying to bank to the left. And I said this a long, long time ago, but banking just means changing your roll. And so that means you want your right wing to go up and your left wing to go down. And so to do that, you move the flight controls, or in this plane it'd be a yoke, you roll that to the left, and that will move the right aileron down to increase the lift on the right wing, and the left aileron up to decrease the lift on the left wing, so that the right wing rises and the left wing falls. But remember that every time we change our lift or create lift at all, we change our drag. So the wings were creating drag before, but now that we've made the lift asymmetrical, the drag is also asymmetrical, and there's higher drag on the side that just got more lift, so the side that's going up, but that's the side that we're turning away from. So we want to roll left, but we're creating more drag on the right. So that's what creates this thing that pulls you the opposite direction. So in this one, we're rolling to the right, so we're banking right. And our left wing is creating more lift, but also more drag. So that means the plane wants to yaw to the left, since there's more drag on this side than on this side, even at the same time as it's rolling to the right. And that yaw, because it's in the wrong direction, is called adverse yaw. And so what we use the rudder for is to actively counter that adverse yaw. So as the nose would try to pull to the left in this turn, you would add right rudder to hold it to the right, but you don't want to turn like farther to the right than you would have otherwise. And so what you're trying to do is maintain what's called coordination, which basically just means that the nose is pointing in the same direction the plane is flying. So like if you don't use any rudder and you try to roll like this, then the nose starts pulling to the left, even though you're flying more to the right now. And so that means you're uncoordinated because the nose is no longer pointing the same direction as the plane is flying, which is like, if you think about the velocity, it's the speed and the direction, right? So the velocity vector is where you're flying. So I'm just going to call it that instead because it's easier or makes more sense or something. So you always want your nose to be pointing at your velocity vector. And if you're coordinated, your nose is pointing at your velocity vector, and you just use the rudder to maintain coordination. So if something happens like wind, or wind doesn't normally do it, like a gust of wind or adverse yaw or whatever that would make you uncoordinated, you just use the rudder to return to or stay coordinated. And there's a little instrument in the plane that helps you make sure you are coordinated. And it's more efficient that way, because think about if you're uncoordinated and your nose is pointing sideways, now you're presenting the fuselage to the airflow and you're adding a bunch of drag from like hitting the fuselage sideways instead of the air just going by it on both sides. So it's less efficient. It's uncomfortable for passengers because it feels like you're like sliding sideways kind of. So yeah, coordinated flight is good. It's kind of hard to do on an RC plane because they're small, but it's still a design goal. So that's the reason we still have a rudder instead of just having a vertical, is you want to be coordinated and sometimes you need to slip and stuff. So the only times you are intentionally uncoordinated is if you're flying in a slip, which means you're intentionally pointing the nose away from the velocity vector. And it's always because you want to add drag on purpose, either because you want to descend faster or slow down while moving, like without descending, or climbing, like you want to slow down and stay level, or you just want to descend and not speed up. But so we use those sometimes. So we need a rudder, and the rudder needs to be part of the vertical tail, aka the fin, and that needs to be sized according to this. So basically everything you need to size the tail is in here. You may have noticed that there's nothing that says you have to have a certain area or moment arm, and that's because you don't. You can choose that. Good luck with trying to pick a value that seems good, but if you, like we've been doing a lot, if you need points of reference, you can look at other aircraft and figure out like what their approximate values are for like that proportion. And also just don't be afraid to like draw it or do like a really rough CAD or something that's to scale, so that you can see like, okay, if I put in like 20 inches, then my tail area is this big. How big does that look relative to the rest of the plane? Because if it looks freaking huge, then you might be outside the, like, or you might be drifting away from what's reasonable, because it's hard to like picture just with the numbers. And other planes, especially if they're the same approximate type, so basically single wing propeller planes that don't go super fast, those can be a good point of reference. That's what I would do if I were you guys. There's more stability stuff you can get into that's at a higher level, but like this works plenty fine for a lot of planes at the initial design stage. So good luck. If you had questions about that, now would be a good time to ask me, because if not, then I'm gonna stop the recording and let you guys get working. Okay, cool. I will be around. Well, okay, yeah, I'm gonna stop the recording because that's all we need to